All right, stat students. So today is going to be the final lesson for our probability unit. Now, there's so many concepts that we've covered, and a lot of students have reached out to me about having some issues with this problem set and the conditional probability worksheet. Keep reaching out to me about those. I mean, I want to put out as much content for you guys as far as working through your worksheets, but I want to make sure you're asking for the help and getting help that you guys need to be successful, because yes, a lot of this content can be kind of difficult. So just make sure that you keep reaching out to me, and I'll try my best to answer questions that you guys have. So today we're talking a little bit more about independence, but let's go ahead and get started. All right, so last lesson, and I now realize this is kind of a weird way to put this, but we had these examples of independent events. The biggest thing was this idea of with replacement, but we had coin flips, rolling dice, spinners. There's all kinds of examples for independent events, and then we'd forgotten to write what makes a dependent event. So examples of dependent events. The main thing that we're really looking at here is the idea where we're saying without replacement. There's not a lot of other situations that I can think of off the top of my head that are dependent. We are going to talk about a new situation today with that, but today we're really going to focus on proving that two events are independent. So what I'd like you to do is draw a line in your notes, title the section with this. Let me make that a little bit larger. And we're going to say proving two events are independent, because here we have, it says this following table compares the hand dominance of 200 Canadian high school students and what methods they prefer to communicate with in their field. So not on our list would be this example here, the preference for communication and left-handed, right-handed. So let's think about our definition of independent. Does knowing one outcome, like knowing that you're left-handed or right-handed, does that help me predict the way that you're going to communicate, either in person, online, or cell phone, text? Initially, your thoughts are no, but it's not as obvious as like a coin flip or rolling a dice. So that's the key idea, is there are situations that occur that are not listed here on this list that I've created for you. The list that I've created for you is like you seeing it in a problem and knowing that, oh, that's independent, or oh, that's dependent, whether it says with replacement, without replacement, okay? But in this situation, we don't have that. We're not really sure, okay? So this comes straight from the problem set. We're using this table here. This is number 65. It says, which of the following statements supports the conclusion that the event right-handed and the event online are not independent? So in our notes, we had written, where did I put that? Here it is. We had written this rule here, and this is what we need. Okay, so let me go ahead and copy that in here, because we need this rule. And initially, this rule looks kind of like, well, it looks kind of confusing. And that's just sort of how a lot of these rules have looked when we first encountered them in this chapter. But we need this rule. Okay, and it said, so we're trying to show that what this rule is saying. Let's analyze it a little bit. Given that the first event happened, B, remember that's our given that statement. We really talked about conditional probability. If the event occurs, it shouldn't change the probability of A, okay? Because that's what we do in conditional probability. Look at this part. If this part here, if A goes unaffected by B, then it should just be A. That's how we're interpreting this formula here that's going to help us prove independence or not, right? Now, they've told us that they're not independent, but this we're trying to show it based on the formulas here. So let's rewrite this, and in your notes, you just need to, you don't have to write like the whole scenario. Just write up this formula first, and we're going to say number 65. This is the work for 65. It wants to know right-handed and online. So we're going to start this probability. We're going to say right-handed, given that they are online, is equal to the probability that they are right-handed. All right, added the background music. Okay, so this is what we want to show. Or we could show it the other way. So we'll write both up, okay? So go ahead and write this one up. We're just flipping them. Online, right-handed equals online. So either way, those are going to be what we want. So we know our rule for conditional probability as well. So we know this is right-handed and online over probability of online. Now we can go ahead and find the probability of right-handed. Well, how many right-handed people are there? There's 166 out of 200. So we're going to put that 166 out of 200. Then let's continue. We have this over here. And let's go ahead and create the let's create the other one. So what's our right-handed and online? So that's 51 people. How many people are online? 60. Okay. So all we need to do to show if these events were independent, then these would be the same. So we're going to confirm that they are or are not by turning them into decimals. So 0.85. Is that equal to 166 out of 200? I don't think it's going to be, but we want to check. 0.83, it was close. So these are not equal to each other. So this is showing, okay, that this is proving that these are not independent. So we're going to write that in our notes. Okay, not independent. Sorry you had to sit there and watch me struggle to write that with my mouse. All right, that's what we did. So are there any fractions over here that match this fraction setup here? It looks like E is the one that's showing that these are not independent, and that's just lucky because and here's an answer to maybe a question you have. Do I have to show both? No. If you show it with one of them, you have proven that they are not independent, okay? You don't have to check both. This is just showing that either one could be used to show that these events are dependent or independent. In this case, these events are dependent. Knowing that you like to communicate online does change the probability that you are right-handed. Now that may not make much sense from a practical standpoint, but this is how statisticians and people that work with probabilities, this is the rule that they created. And hopefully it makes sense. Again, let's explain it one more time. If these are independent, that means the definition of independent, knowing this event should not change the probability of A. That means the probability should be equal. For if there's a conditional probability, it should be equal. Okay. Now there's other examples that we can look at to where these will be equal. We'll practice those later this week. Okay. So this is just to introduce the idea. We didn't end up needing this. Okay. We only ever really just need one to show independence or not independent. Okay. Luckily, that was one of the answer choices that we saw right here. Okay. So we have one more topic that I want to talk about, and then we're going to work some examples in this practice set, problem set. Here, draw a line in your notes. The last topic, mutually exclusive versus independent. So here are the two definitions that we need. Okay, and if I had asked you to, you could probably dig your notes, and you would find them. Okay, so let's think about these definitions. First off, two events A and B are mutually exclusive if they have no outcomes in common, so that they can never occur at the same time. When we look at that from a Venn diagram standpoint, the bottom down here, this is when they don't overlap. In a two-way table, the intersection would be 0, okay? So that's sort of our idea of that. Next, independence. two events A and B are independent if the occurrence of one event does not change the probability the other event will happen. Okay, so mutually exclusive versus independent. If I know events are mutually exclusive, what does that mean about independence? Okay, that's what we're going to try to determine right now. Okay, and I always go to this textbook example to explain this. And let me zoom in on this. So we have two events here that are obviously mutually exclusive. So think about it. Could I ever select a male, okay, in the population of the United States or the world? It doesn't matter. This could be any size population you want it to be. And you have a male, the characteristic of male, and then you also have a characteristic of pregnant. All right. Males cannot be pregnant. I know some of you might argue with me on this, but sorry, from our textbook standpoint and from our statistics textbook standpoint, that's what we're looking at here. A male will never be pregnant. Okay? So, with that in mind, if I know you're male, does that help me predict, or does that change the probability that you're pregnant? That's really what we're asking here when we're comparing mutually exclusive, which we know these events are, and then independence. Does knowing that you are a male, the occurrence of one event, does that change the probability, or does it not? If it doesn't change it, then it's independent. If it does, then they're dependent, right? Or not independent. So it absolutely does. Here, let's read what the textbook says here. Okay, and we're actually going to write this down. But let's read this statement. It says, let's start with the new chance process. Choosing a U.S. adult at random. Define event A as they're male, B as they're pregnant. It's fairly clear that these two events are mutually exclusive. They can't happen together, right? So that's what we just said. What about independence? If you know event A has occurred, does this change the probability event B happens? Of course. If we know the person is male, then the chance the person is pregnant is 0, right? So if you have a mutually exclusive event, okay, can't happen at the same time. If there's a mutually exclusive event, that means automatically if one of them happens, the other is not. Like it tells you the probability of the other immediately. Okay? So that's the idea of independence. Knowing one event helps you predict the future chance of the other event. Okay? If you think about dice rolls, if I know the first roll is a 6, it does not ever affect the next roll, like ever. It doesn't change the probability of getting a 6 again or any other number for the second roll. Those are why those are independent events. If I take a card from a deck of cards and I know that the first one was red, if I don't put that card back with replacement, that does change the probability of getting another red or change the probability of getting a black. So that's this whole idea here. And a lot of times this can be kind of confusing, but hopefully you're able to remember this rule. Two mutually exclusive events can never be independent, because if one event happens, the other event is guaranteed not to happen. This has to go in our notes. So let's go ahead and let's put that in there. Paste. Boom. Increase the text size. Didn't happen. Hold on. There it is. Bold it. You guys need to write this. We're going to pause the video so that you can write this down. And then we're going to apply this immediately just because we need to. So go ahead and write this down. Two mutually exclusive events can never be independent, because if one event happens, the other is guaranteed. Example, male and pregnant. That's a good example of mutually exclusive events, like a really good example. Mutually exclusive events, and they're not independent. Let's look at the problem set. All right, so we get to use this rule immediately, going back to number 22 and 23. So I said, I think earlier on, you'd be able to attempt 20 all the way through 27 or something, but really 22 and 23 couldn't be done without this rule, okay? Actually, 22 could be done. So 22 is not the one that I'm talking about, but I remember I tried to work these on for distance learners, and it just didn't work out. So let's try these questions now. So if A and B are disjoint, meaning mutually exclusive, the probability that they both occur is what? Well, that's our definition, right? Like we just wrote that down. It's 0, right? If they're mutually exclusive. So there's our rule. So again, a lot of this probability chapter is going to be based on these rules. So A should be the right answer. But now here we go. 23. if event A has a probability of 0.4 and event B has a probability of 0.5, and A and B are independent, what is the probability both events occur? Well, again, our definition is going to save us on this one, and I'm not using this disjoint rule just yet, so I need to find that problem. But we have our rule here. Actually, wait, no, we don't have that. Hold on. It's this one, multiplication rule for independent events. This is actually on your formula sheet that you're allowed to use on the test. But let's put this rule in here. Wrong slide. Hold on. Next, go here. Okay, so here's the rule that we need. So if we know the events are independent, so we have to see that these are independent, and it does clearly state that here on number 23. All we have to do is multiply them. So all I'm going to do is probability of A times probability of B. Now, we can only do that if we know that they're independent, okay? They have to be independent. So our solution to this is 0.4 or 0.5 times 0.4. I guess order doesn't matter. So 0.2 should be the answer. Let me find another example where we have to use this these rules from here that we just wrote down, okay? So give me 1 second. Okay, embarrassingly, I could not find an example that talks about using the idea of mutually exclusive to prove dependence or what have you. So anyway, this is an important rule to tie those two together. But let's do one more example that's a little bit different. Question 11 in your homework that's due Wednesday. Let's see, the 18th. So tomorrow, as far as my calendar looks. This is a very difficult problem on our conditional probability worksheet. Okay, it talks about having an illness and not having an illness. So let's look at an example in the problem set that is very close to that, because on this sheet I said a lot of you should be using a two-way table to model it. And if I have to later this week, I can go through this, or maybe tomorrow, excuse me, since it's due tomorrow. That's something I could put up a solution path to number 11. But maybe this example here can help, okay? So it says the probability of a randomly selected adult having a rare disease for which a diagnostic test has been developed is 0.0001 or 0.001. The diagnostic test is not perfect. The probability of the test will be positive, indicating the person has a disease, is 0.99. For a person with the disease, 0.99 for a person with the disease and 0.02 for a person without the disease, okay? So this is going to be a sequence of events. You have the disease and you go get a test and it gets a result. So this is going to be, whenever you see anything about like diseases and stuff, it's going to be super helpful to use a tree diagram. So on number 11 on this conditional sheet, I would recommend using a tree diagram, okay? So that's what I'm going to start. So let's go ahead and we can do this in our notes. Or whatever sheet that you're doing your problem set for, you can do that. So first off, somebody's either going to have the disease or they're not going to have the disease. So we say disease or not the disease. Next, they're going to take this diagnostic test, and they said the test is not perfect. Okay, a lot of tests, if you think about like COVID-19 tests, you've heard this idea of like a false positive. That happens. And that's just part of testing. They're not perfect. So usually you want to get multiple tests to improve your accuracy, okay? So it says, the probability of the test will be positive, indicating the person has the disease, is 0.99 for somebody with the disease. So if they have the disease, it's going to show positive 0.99. So we're going to put that, 0.99. Now that means negative would be 0.01. I forgot I like to type on these. Anyway, next. So 0.02 positive. So this would be called a false positive. You may have heard that term this year with COVID-19. What's the false positive rate? Well, this is what they're talking about. So for this disease in particular, it is 0.02. That's the false positive rate for this disease. Okay? That means that the false negative rate is 0.98. Or excuse me, this would just be negative. This would be true negative. Okay, so 0.98. Now what goes on these first branches? What says the rare disease is 0.001. That's the probability of having that rare disease. So 1 in 1,000. I feel like it could be rare. That means that 0.999 would be the probability of not having this disease. Okay, so we've got our sample space created here. Now it says, what proportion of the adults would test positive? Okay, well there's two spaces where they could test positive. That is here and here. And we've explained how to use these tree diagrams, and that we have to multiply the branches to get our values. So let's go ahead and do that. We're gonna do 0.001 times 0.99. That's a very small number, so 3 zeros and then 99. So we're gonna put that 0.12399. That's gonna go there. And then we also want to find this one, so we need 0.999 times 0.02. So this is the false positive rate. So I can actually copy this, I think. Oh, that's nice. Boom. Okay, so we have the true positive rate here, given that you have it. So actually what this means is the probability that adults would test positive. Just in general, this is those with the disease, and this is those that don't have the disease. So what we need to do is combine these to get the answer. So it actually isn't either of these, even though it looks like it. We have to add these together. So let's do that. Plus 399. Yeah, there we go. Okay, so adding those together, we get our probability here. So we just have to make sure that we remember this is the percent of the population that will test positive taking this test. Okay, regardless of if they have it or not. That's what I meant to say. All right, next, if a randomly selected person is tested and the test result is positive, the probability the individual has the disease is, okay, so what we have here is a conditional probability. And hopefully you can see that when, as I read it, it says if a person has it, so that's telling us we already know that they have it. So we're gonna use our formula. Given that they tested positive, okay, they got a positive result, what's the probability that they have the disease? So what's the probability they have the disease? So we're going to use our formula, probability of disease and positive over probability of positive. So that's going to be, that's what we want right there. We want to have that. So what is the probability of disease and positive? Well, that is this value here. So we're going to put, I'm actually just going to duplicate that there, and we're going to divide that by what's the probability of positive? Well, that's actually what we found up here. The point, so that's that was our answer for that first problem, 0.02097. So that goes on the bottom, and this is going to get us our answer here. So hopefully that makes sense. The and statement, which is multiplying this, that's what is actually on these, the and statement. It's this times this gets us this, okay? And then on the bottom, it's just the probability of positive, which we found earlier. We had to find both, the overall probability of positive. So given that you tested positive, all the positive cases, what's the probability you have the disease, right? That's up top, okay? And we could represent this in a two-way table. I'm going to show that actually, but let's go ahead and find the answer to this. So we're going to do, we need 0.00099 divided by 0.2097. All right, and we're going to round that. I don't know if y'all can see that. There you go. So E is going to be the best choice for this. That's our answer. Now let's show this in a two-way table, okay? So let me go ahead and construct one. All right, so I've set mine up here, and let's talk about this. The two-way tables and the tree diagrams, they can be compared to one another, but not as easily as, say, a Venn diagram. So we know that these probabilities here are going to be on there. So the probability of disease is 0.001, and the probability of not having the disease is 0.999. which adds up to 100%. Now the probability of positive, we have two spaces where that occurs, so we had to add that. That's going to be this right here. Let me actually just so I don't have to write as much, let me just copy that. We'll put that here. So that goes there. And then to find this, of course, we have to subtract. So 1 minus 0.02097. So this is going to go in here. So there's our probability. Okay. We don't see that anywhere on here, but it would be, if we wanted to find it, it would be the addition of these two spaces that are now right, they're blank. Now, do we have this value here? Yes, we actually have that. That's going to be this value here, the 0.0099. So let's duplicate that. Okay, so that goes here. And then we have this value as well, which is this one, right? Because this is where it's not, they don't have the disease and they test positive. So it's this one here. We got to duplicate that right there. Okay. Now the negatives here, we can just find by subtraction, or we could do the multiplication. So I'm going to actually do this. We're going to put 0.999 times 0.98. This value should go right here. That's what should go there. And actually this value is going to go here. Okay. And if I wanted to confirm that, let's make sure that that's right. Hopefully I didn't do that wrong. 0.99, take away, let's take away this one, 0.01998. Yeah, you can see that those match up right there. Okay. And then to find this one up here, I'm going to do 0.001 times 0.01, teeny tiny number, but it is going to go here. Duplicate it right there. Tiny number. But if we add it, you'll see it will get us this one here, right? So that does work. It should work. And then add it. Look here. We can see that these two add up. If you add them together, they work, right? So pretty cool how these decimals all work. But that's how we would relate this. So this is the inside of the table. The inside of the table occurs here. Oh, wow. No. The inside, getting all these shapes I don't want. Rectangle. The inside of the table is here. All these values are inside. Then we add up the negatives to get the totals, positives to get the totals for positive. These are already going to be on that margin there. Okay. So that's relating those together. You should try this method with the two-way table or with the tree diagram. You can make it work with a two-way table. It's just a little more challenging. But try that on the conditional probability here for number 11, and that should help you out. Okay. All right, we're 28 minutes in. I'm going to go ahead and stop here.